Hi everyone, this is James and welcome back to my channel. Finally, we have arrived in IB Maths AASL Topic 2, Functions. Timestamps are also in the video description, so you can just jump to whatever part you want to watch. We'll be covering the IB Maths AASL syllabus, which can be found online if you just search up IB Maths AA syllabus, or I've also linked it down in the description below. So without further ado, let's begin. Now, beginning with SL 2.1, this topic is about the different forms of the equation of a straight line, and what we're talking about are these three equations right here. So if we're graphing a straight line, we'll have, for example, we'll have a Cartesian plane like this, right, with our x and y axes, x, y, and basically a straight line graph will look something like this. Assuming it is straight, it will look something like this, right? And it will have an equation. And what that equation means is, for example, the equation is called y equals 3x minus 2, right? What that means is, say that we are given x equals 2, and we're looking at this point right here. If we want to graph that onto our graph using this equation right here, we simply need to substitute 2 into this equation, and we'll get 3 multiplied by 2, which is our x, minus 2, giving us 6 minus 2, which is 4. And we plot our point based on the x and y value. And if we do that for every single number, we'll find that we have a straight line. IB wants you to know and distinguish between the three different ways that you can write an equation of a straight line. Now, you also are expected to remember the names, because sometimes they'll ask you in the question, it's given in this form or express it in this form. But that's pretty rare, but just in case you wanted to learn it, the first one is called gradient intercept, second one is called general, and the third one is called point gradient. Okay, so before we try to understand what the difference between the three equations are, let's first try to understand what a gradient is. And this term is actually replaceable by other terms such as slope. You might have heard of it being referred to as slope. Or this equation, instead of y2 minus y1 on x2 minus x1, you might have heard of it being written as rise over run. And it all means the same thing. So what a gradient is let's say we're given a straight line on a Cartesian plane like this. The gradient basically refers to, the gradient basically refers to how much this line is sloping. So if we have a flat horizontal line like this, the gradient is 0 because it's not increasing or decreasing, even though the x values are increasing. Right, so this is our x and this is our y. But for this function right here, it has a positive gradient, because every time x increases, let's say it increases by 1, 2, 3, like this, right? Our y values also seem to increase by a fixed amount. So that's what a gradient is. It's the ratio of how much your function, how much your point rises in terms of the y-axis for when the x values increase. And this is why you can actually calculate it if you're just given the graph or given just 2 points on the graph, because you're able to use either of these formulas right here. This is the same thing. And to keep it simple, we'll use the one in the data booklet, which is just y2 minus y1 on x2 minus x1. Say we are given this point right here. This is on the line. It is, let's say it is 3, 3. Let's just take this point. Let's say it is negative 1, negative 1. Okay. And assuming it goes through the origin of this graph, it would. Now, how we calculate the gradient of this graph is we want to take the y, so we want to take 2 points. This is our first point right here, and this is our second point right here. So our first point would be x1, y1, and in this case, we can take it to be negative 1, negative 1. Right? That will be the point that we pick over here. And our second one for x2, y2, let's take the second point that we know, 3, 3. So if we want to find m, or the gradient, we simply need to substitute y2, which is 3, minus y1, which is negative 1, on top of x2 minus x1, which is 3 minus negative 1 again, because the x values respectively for x2 and x1 are 3 and negative 1. And we'll find that negatives become positive, so it becomes 4 on 4, and our gradient is 1. And what this value right here actually means is for every increase in our x value by 1, our y value will increase by 1. And that can be seen here because it goes through the origin, right? So if we increase our x value by 1, our y value will also increase by 1, making this point here 1 and 1. And then it keeps on going, it will be 2, 2. And you can basically visualize it like that. So that's what a gradient is. So now that we know what a gradient is, let's define the term intercept. What the word intercept means is when the graph intercepts or goes through one of the axes. And in this case, C stands for the y-intercept in the gradient intercept form, right? So if we have this graph right here, it intercepts the y-axis at y equals 0. Or if we're given a graph like this, for example, we can see that the graph intercepts the y-axis at a positive number right here. So it intercepts the y-axis at, let's say, positive 1. Right? This is where it intercepts the y-axis. And that means for this graph, if we were to use our first equation right here, y equals mx plus c, doesn't matter what m is equal to, but our c value will be positive 1. And now that we know intercept and gradient, these three equations will make a lot more sense. The first one is called the gradient intercept form. It includes m, which is the gradient, and c, which is the y-intercept. So if you're given a graph and you're able to work out the gradient by using this formula right here, and you can identify what c is equal to by just looking at when it intercepts the y-axis, you're able to define the straight line in terms of this first equation right here. Now, the point gradient form, which is this one right here, is another way of expressing a straight line. And that can be used when we know the gradient and also the coordinates of one of the points. And finally, this general form right here, this is generally given in a question, which we can use to convert to the gradient intercept form, or we can convert something from the gradient intercept form to the general form. Now, there are some similarities between these two equations right here, being if we have a point gradient form, I'm just going to sub in some random numbers here, and like this, right? If we substituted our m and also a points into our point gradient form, and we expand everything, we'll find that it will just equal, in this case, if we add 1 to both sides, it will equal 2x minus 1. And this is actually back into our gradient intercept form. We started with the point gradient, but after simplifying everything, we ended up with our gradient and -1 being our intercept. So these are actually interchangeable. So you can actually convert the point gradient form into the gradient intercept form. And this is similar for the general form. For example, if we want to convert the gradient intercept form into the general form, let's say we're given this equation right here, and we wanted to convert it into the general form, well, ax must be at the front, so ax, right, plus by. In this case, if we want to minus y to both sides, we will get 0 equals 2x minus y plus 3. And notice here, this equation right here is equal to 0, and it is in the form ax plus by plus d. And this right here is the general form. So there's a lot of commonalities between the equations, but overall, usually you'll know which equation to use because either the question will tell you, or you can base your working on what information you're given and work from there. Okay, now moving on to SL 2.2. We're going to do all of the practice questions at the end in this video because I couldn't really find any questions that just related to only 2.1 because it is a pretty simple topic. So we're just going to try to finish all of the syllabus statements before we move on to a couple practice questions which encompass all of the subtopics that we've covered in this video. In SL 2.2, we want to identify the concept of a function. We want to know what domain and range is, and also we'll need to distinguish and work out these things from a graph, or vice versa, we're given these guys and we want to graph it. We also need to learn function notation, and lastly, we also need to know what inverse function means. So let's begin with a function. A function, this is the most standard function, f of x. X is the variable that we give it, right? And f is something that we are going to do to our variable. So f of x, it could be something, for example, like 2x plus 1. And in this case, x is our variable, and we are going to be doing two things to it. We're going to be multiplying it by 2, and we're going to be adding 1 to it. That is the function that we are going to apply on x in order to achieve a graph. We actually already know how to plot a straight line. It's just we never thought about it in terms of a function. So in this case, we could actually just visualize it as being y equals 2x plus 1. But we define it as f of x this time. So for example, instead of writing y, we will write f of x. And over here, we can just write x, right? So for every x value, let's say x equals 1, our y value here will be 2 times 1 plus 1, which will be 3, right? It will be 3. meaning this will be one of our points. And our graph might look something like this. So again, it's just a straight line graph, but we've defined it in terms of a function. And we can also notice that our variable doesn't have to just be f of x. It could be v of t, for example, written right here, right? And what that means is it could be a velocity function over time, where our x-axis is called t for time, and v of t is our velocity at that time. And it could still be defined as 2t plus 1, right here, v of t equals 2t plus 1, and it would look the exact same as well. But again, it's just a different way of writing out the same concept. So that's what a function is. So now let's understand what domain and range means. So we have domain and range. All we need to know is that domain stands for the x-axis and range stands for the y-axis, okay? And what it means is the domain and range, if we think about those words literally, it just means how much we encompass or how much we cover, right? So if we're given a function like this, and I'm going to be calling the lines functions now, or any sort of graph a function from now on. If we're given a function like this, and it keeps on going, and the domain will be infinite, because if we think about it, a domain is x value, right? So we have the x-axis right here. This is the horizontal axis. And if this graph were to keep on going, it would go all the way back until negative infinity, and it would keep on increasing in the positive direction until it reaches positive infinity. And if we think about the same graph, the range means the y values. That means if we're looking at this axis right here, the vertical axis, and if this graph were to continue all the way over here and all the way over here, the y values will extend into positive infinity and also negative infinity. And we can express the domain of our function like this. Negative infinity is less than x, which is less than infinity. Now what this means is that the x values of our function extend from all the way from negative infinity to positive infinity. And these signs right here are, you can either think of them as less than signs, or altogether they are called inequalities, because it's not an equal sign. And notice I didn't actually put this over here, this little line. That means it will be less than or equal to. But you can't have x equal to negative infinity. So whenever you're referring to infinity, we cannot have equal signs. So that's why it's just less than, not less than or equal to. And if we think about it the same way in terms of range, the range of our function right here, if this were to go on infinitely, it would go from negative infinity to positive infinity as well, right? So it would actually be the exact same thing, except we substitute the x for y, because in this case we are looking at the vertical values. And now the second way of expressing this, I'm just going to write the equivalent sign. The second way of expressing the domain and the range of our function is we can use a thing called interval notation. Now what interval notation is, I'm just going to write out the first example right here. It will look something like this. Now this may look like a coordinate, but it's actually our domain. So we can express it like this, d colon, or just write domain or anything like that. The first number that we put in our brackets refers to our lower boundary, and the second number after the comma will be our higher boundary, or upper boundary. And that essentially means the same thing, because it means from negative infinity to positive infinity is our domain. And another way of writing the brackets is that we can use square brackets. However, in this case it's inappropriate, because what the square brackets means is greater or equal to. So let's say this over here, let's just say our domain was negative 3 to positive 2, right? And it's including negative 3 but not including positive 2. Then we can write that as inclusive, because it's a square bracket, it means inclusive of our lower boundary, comma, and exclusive of our upper boundary. So that's when we use our square brackets as opposed to our round brackets. So now finally the range will be equal to negative infinity to positive infinity as well. And we're going to be using round brackets because it doesn't actually include negative and positive infinity. How we visualize these domains on a graph is sometimes we'll be given a graph something like this. Let's say we're given a graph like this. And these little circles at the end basically represent, they mean at that point the graph stops, okay? So let's say this point right here is negative 2, negative 2, and this point right here is positive 3, positive 4, right? That means our graph, the domain of our graph will be from negative 2, because it's our x values, to positive 3. Meaning we can write it as let's just write domain, and I'll just use interval notation right here, but it actually means the same thing. You can write it either way. Our domain will just be from -2 to +3, and our range will be from -2 to +4, okay? And now we have to add in our brackets. So what kind of brackets do we use? Well, notice that the two circles right here, one of them is filled in and the other is hollow. That's a way of expressing functions. Because if we're just looking at a function and it stops at this point, how do we know whether the function actually includes that point or it's just infinitely close to that point but it doesn't include it? Well, if it's a filled in bracket, that means it's inclusive. That means it actually includes that point, which means we can actually use our square brackets here to show that our domain includes -2. However, when we reach +3 right here, our upper value for our domain, it actually is a hollow circle, meaning it doesn't include the term. So we have to express it with a round bracket. And same for our range. Our lowest y value is -2, and it is a solid filled in circle. So we use square brackets to indicate that it's inclusive of that point. And for our upper y value, it is equal to 4. However, it is a hollow circle, meaning it doesn't actually include that point, so we have to use round brackets. So here is our domain and range in interval notation for this function. Now, just a quick note, domain and range is looking for all of the x values and y values. So if we're given a function like this, for example, our range isn't just going to be from here to here. It's not the first point to the last point. It means all of the y values, meaning we have to consider from here all the way up to here. That will be our range instead of just the first to last point. And that goes the same for if we're given a function which breaks apart in the middle like this, then our range would still include everything, right? So let's say it's something like this, right? Then our range would be, we have to consider our range going from here to here with also here to here, meaning we have to have two sets of ranges, meaning our range would be equal to, let's say, -4 to -2, including +2 and 3. And if you were to write it in this form right here, inequalities, then you would have to address that there are two sets as well, either by using the union sign or just writing all of the ranges out. Okay, now moving on to inverse functions. If we are given this function right here, 2x plus 1, and it will look something like this, right? If that is our function f of x, our inverse function would just be the exact same function, but reflected off y equals x. And how we can understand what that means is if we have a function like this right here, and what y equals x looks like is that it's just a straight line which goes through the origin, and it has a gradient of 1. Okay, so it will have the points 1, 1, 2, 2, 3, 3, etc. And to find the inverse of the function, we basically flip it like a mirror. We flip it over that y equals x line. So in this case, if this was our original function, we would have to flip it, and this is just a rough sketch, but it would look something like this. And this right here would not be f of x, it would be the inverse of f of x, or f -1 on the top of x. And for an inverse function, the domain and range will flip. And what I mean by that is, say we are given a function which looks like this. If we were to take the inverse, it would look something like this, right? And what happens here is that our range of our original function, which is from here to here, actually becomes our domain of our second function, which is from here to here. Now that is a little bit hard to visualize, but that is a common property for any inverse function, which we have to keep in mind, and we'll be using that property in a lot of practice questions as well. And now finally, 2.3 is a relatively simpler dot point. It's just going to be about graphing a function based on the equation, or the other way around. We're given a function and we are asked to find the equation of that function. And that's pretty much it for 2.3. Okay, now moving on to a practice question. Here we have the function f of x equals e to the power of x plus 3. And we want to show that the inverse of our f of x is equal to ln x minus 3. So this is a question testing our knowledge on inverse functions. And how we can work out what our inverse function is equal to based on the original function, which we have right here, is we can set every variable equal to y. Because as we know, an inverse function basically means we're flipping all the x values for the y values and all the y values for the x values. So if we substitute f of x into f of y, that is actually the same thing as our inverse of our x function. So this is the same thing, right? And this would be equal to, if we substitute y into our equation, into our function, and we replace every x value with a y value, we will find that f of y is equal to e raised to y plus 3. And now f of y will be equal to x, because we are substituting the original function, which is y equals e to the power of x plus 3, into x equals e to the power of y plus 3. So this is what we're going to have to write over here, meaning our new function would be x equals e to the power of y plus 3. And this is our inverse function, right? And we want to show that f of inverse of x is equal to this. And if we want to find the inverse of something, we have to rearrange the function so that y is on its own. And how we can do that is we can take the inverse operation of raising something to the power of e. And we know the inverse of raising something to e is the natural log, as we established in topic 1, right? So we know that ln of e to the power of something, let's say ln e to the power of x, is just x, because ln just means log base e of e, right? So we can move the x to the front using our log laws, and log base e of e is just 1. Because what log base e of e means is we have to raise e to the power of a number which equals to e, right? We're raising e to a number which equals to e, and that number must be equal to 1. So therefore, they are inverses. So in this case, if we take the natural log of both sides, we get ln x equals to ln e to the power of y plus 3. And the ln and e are inverse operations, so they cancel out. And we are left with ln x is equal to y plus 3. Take away 3 from both sides, ln x minus 3 is equal to y. And this right here is our answer to part A1. And now for part A2, we want to find the domain of f of the inverse of this function. So we want to find the domain of this function right here. So there are two ways to solve this question right here. One is we recognize what ln x is, what ln x minus 3 looks like, and we establish what the domain is. Or we can figure out the range of our original function, and that would be the domain of our inverse function, because the range of your original function will be the domain of your inverse, and vice versa. The domain of your original will be the range of your inverse. So you can solve it either way, but for now I'm just going to use the inverse function by itself. We should know that a logarithmic function would look something like this, where it approaches negative infinity here on the y-axis, but it actually never touches negative infinity. And over here on the positive side, it's just going to keep on increasing in both the y and x values indefinitely. Meaning, if we want to find the domain, we need to recognize that the domain, the lowest value for x, would just be 0. However, it doesn't actually include 0. This is why we use the round brackets, because it approaches 0, but it never gets it. So that's why we use round brackets. And the upper value would just be infinity, because it will go on in this direction forever. So the domain would be infinity. And the cool thing about this question is that this minus 3 here actually doesn't affect the domain, because by applying minus 3 to the function, it would just look something like this. It would just be 3 lower. However, what that does to the function is that it decreases all of the y values by 3. But that doesn't actually affect the domain, because domains only look at the x value, which is why we are just able to solve for the domain just looking at this. But you can also solve it all together, because it would have no effects either way. You just need to recognize that that's the case, and the domain is therefore from 0 to infinity, and it doesn't include 0 nor infinity. Part B, we want to solve the equation the inverse of f of x equaling to ln 1 on x. And we know what the inverse of f of x is based on part AI here. It will just be equal to this. And this is equal to ln 1 on x. So this is more of a logarithmic question, but we're going to solve it either way. How we can solve this is we need to recognize two things. Firstly, these ln, the natural logs here, make it a lot harder for us to solve the question because they're in the way. So how we can get rid of the natural logs is we can relate our concept back to inverse functions or inverse operations. And we know that the inverse of a logarithm would just be the base, would just be writing the base and raising it to the power of the logarithm. What I mean by that is e to the power of ln x is equal to x, because ln x basically means a number which we raise e to equal x. So the whole ln x would just be that number which we need to raise e to equal x. And this concept is further explained in my topic 1 video, but in this case we just need to remember that ln and e are inverses, so this would just equal to x. Therefore, we can raise e to the power of everything, both the left and the right sides, in order to cancel out the logarithms. So we'll get e to the power of ln x minus 3 equals e to the power of ln 1 on x. And on the right side, it's a lot simpler. E and ln just cancel out, so we're left with 1 on x. On the left side, we use indices laws, and we recognize when there is a minus sign in the indices, we can separate that out into a division of two numbers with the same base. So in this case, it would just be equal to ln e to the power of ln x divided by e to the power of 3. And there's no minus sign here because divide just means negative in terms of indices laws. So e and ln cancel out here, so it would just be x divided by e to the power of 3 equals 1 on x. And now we do cross multiplication. We times both sides by x to get x squared, and we times both sides by e cubed to get e cubed over here. So we'll get this equation right here. And lastly, if we simplify it by square rooting both sides, we'll get x is equal to e to the power of 3, all square rooted, or we can write that as e to the power of 3 on 2. So this right here is our answer to part B, when we have successfully solved this equation, finding what the variable of x is equal to. Okay, moving on to another practice question. The following diagram shows the graph of y equals f of x, and this is the domain right here. So we're given this domain, and what we need to pay attention to is that the inequality signs are less than and equal signs, meaning it is inclusive of the endpoints over here, so I'm just going to indicate that by drawing some solid circles over here. What this question is asking for is, we know what f of x is. F of x is this function over here, right? We're given that. And what it's asking for is, if we were to substitute x for -3, what would the function be? Or in other words, when x is equal to -3, what would f of x be equal to? In this case, what would f of -3 be equal to? And how we solve that is we look at our -3 for our x value. In this case, this is our -3 for our x value right here. And we correspond that to the y value that we are graphing, because y equals f of x. So in this case, here is x equals -3, and we look at which y value that corresponds to, and we'll find that it equals -1. So f of -3 is equal to -1. Part AII, we want to write down the value of the inverse of f of 1. So what that means is, let's say we are given the inverse function, it would look something like this. And we want to find what y equals to on this graph for when x is equal to 1. Or if we don't want to sketch out what the inverse looks like, we can actually just take the y value of our function and correspond that to the x value. Because what an inverse means is the y and x flip. So usually if we were just asked to find f of 1, we would look at the x value and we would try to find the y value, right? But in this case, we are asked to find the inverse of f of 1, so we want to find the y value and therefore correspond it to an x value. And that would be our y value of our inverse. Hopefully that made sense. So in this case, the inverse of f of 1, we want to look at the y value of 1. So when does the y value of this function equal 1? In this case, is this point right here, because the y value is equal to 1, and correspondingly, the x value is equal to 0. So the inverse of f of 1 is equal to 0. Part B, we want to find the domain of the inverse of f. How do we find the domain of an inverse? Well, from our knowledge of inverse functions, it will be equal to the range of our original function. So what is the range of our original function? Range means the possible values of y which exist within a function. And in this case, the lowest y value that we have is y equals -3. And the highest y value is y equals +3. And we can determine that by just looking at the graph right here. And since the inequalities indicate the inclusiveness of the 2 points, the domain of the inverse of f would simply be with square brackets from -3 to +3. Meaning this graph right here, in terms of y values, goes from -3 to +3, including both -3 and +3. And lastly, on the grid above, sketch the graph of the inverse of f of 1. And how we do this is we want to draw out our line for y equals x, and it would look something like this over here. There you go. So this is y equals x, and we need to mirror our graph over this. And how we can mirror it perfectly is I usually like to just look at the endpoints. Because an inverse flips the x and y values, this point right here, we know it to be 5 and 3, meaning our endpoint for our inverse function would have to be 3 and 5. Okay, so we look at 3 and 5. So here's 5, here is 3, so 3 for x and 5 for y, meaning the point is going to end here. And now same for our beginning value. Well, actually in this case we can just identify it's right here because we just flip it. Or to be on the safe side, we can see, oh, it will be -4 to -3. That is our coordinates of our original, meaning our inverse would have to be -3 and -4, and which it is right here because it's -3 for x and -4 for y. So these are our 2 endpoints. And now the next step is just to look at any points that intercept distinctly, because this is a graph that curves. So if we have a point right here like this clearly intercepts this point right here. We're not sure if it exactly intercepts, but it's close enough. So we can flip the coordinates. In this case, the coordinates are -3 and -1. We can flip that and we can look at this point right here. This is -1, -3, right? So we connect these guys. And now the next point would be the y-intercept. So it intercepts the y at 0 and 1, at the point 0, 1, meaning we would need a point at 1, 0, right? So here is 1, and here is 0, so it will have to intercept there. And now we just connect these dots. And where the original function intersects y equals x, the inverse function must also intersect. So we connect that to here, and we just connect it to the last point. There we go. And now, from the perspective of our y equals x line, we can clearly see that our original function f of x and our inverse function are mirror images, hence inverse functions. And that is the answer to part C. Okay, thank you all for watching. Today we covered topics 2.1, 2.2, and 2.3. Now these subtopics set the foundation for all of the functions topics to come, which is why they may be a little bit easy. So I hope you enjoyed watching this video. Stay tuned for future IB and gaming videos, and yeah, keep studying, keep playing, keep having fun, and IB will be yours to conquer. Oh. See ya!